So students, in this lecture we will see what is positive real function. So any function fs which is equal to ns upon ds is said to be positive real function if it satisfies certain conditions. These conditions are: number 1, the denominator of the function fs should be Hurwitz polynomial. Number 2, if function fs has poles on the j omega axis, then its residue should be real and positive. Number 3, m1 j omega, m2 j omega minus n1 j omega, n2 j omega should be greater than or equal to 0 for all the values of omega, where m1 is the even part of numerator, m2 is the even part of denominator, n1 is the odd part of numerator, and n2 is the odd part of denominator. So let's take an example. Suppose we have to find whether this zs, which is equal to 2s square plus 5 upon ss square plus 1, is positive real or not. Now, first condition for the function to be positive real is the denominator of the function should be Hurwitz. So in this case, the denominator is s square plus 1, that means s cube plus s. For the polynomial to be Hurwitz, all the coefficient of the polynomial should be positive and all the terms should be present. So, but in this case the terms are missing. So second condition is applicable. If there is any missing term, in that case either all the even terms are missing or all the odd terms are missing. In this case all the even terms are missing, that means ds is odd in nature. So ns upon, we will do the continued fraction expansion of this odd component upon its derivative. When we expand this function using continued fraction expansion, we will see this is the odd component. Derivative of its odd component is 3s square plus 1. When we expand ns upon its derivative, we see that all the quotient of this continued fraction expansion is positive. Because all the quotient are positive, that means this ds is a Hurwitz polynomial. Now because first condition is satisfied, we will proceed further for the second condition. Second condition is only applicable if the poles are lying on the j omega axis. When we draw the pole 0 plot of this function, poles are the roots of the denominator, and because the order of the denominator is 3, that means 3 roots will be there. That is 3 poles are there. P1 is lying at origin, P2 and P3 are lying at plus minus J1. When we plot it in the pole 0 plot, the plot will be like this. Because all the poles are there on the j omega axis, that means second condition is applicable. What is the second condition? Second condition is if the poles are lying on the j omega axis, then their residue should be positive. That means when we expand the function using partial fraction expansion, the constant which is related to the factor which is defining pole at the origin should be positive. That means in this case all a, b and c should be positive. When we solve it out and find out the a, b and c, a is equal to 5, b is equal to minus 3 by 2 and c is equal to minus 3 by 2. Because b and c are negative, so zs is not a PRF, not a positive real function. Once any condition gets unsatisfied, it's not necessary to further proceed and check the third condition. So we stop it here only, and the function zs is not a positive real function. Let's take another example. We have to show that the function fs, which is equal to s plus 2 s plus 4 upon s plus 1 s plus 3 is a positive real function. So now again the same condition 1 is denominator must be Hurwitz. The denominator of the function is given by s plus 1 s plus 3. When we check for the Hurwitz polynomial, all the coefficients are present and all are positive. So condition 1 is satisfied. Condition 2 is not applicable because no term is missing. Condition 3, odd upon even or even upon odd depending upon whose order is higher. Here in this case, even term is equal to s square plus 3 and odd is equal to 4s. So because the power of this even term is more than the odd, we will expand ms upon ns. When we expand it using continued fraction, we see that both the quotient are positive. Because both the quotient are positive, that means ds is Hurwitz polynomial. Now second condition is only applicable when the poles are lying on the j omega axis. When we find out the poles, because the order of the denominator is 2, that means 2 poles will be there. P1 is lying at s is equal to -1 and P2 is lying at s is equal to -3. So no poles are there on the j omega axis, so second condition is not applicable. Condition 3 is m1 j omega m2 j omega minus n1 j omega into n2 j omega is greater than or equal to 0 for all the values of omega. m1 is the even part of numerator, which is equal to s square plus 8, as we can see in this function, can be written as s square plus 6s plus 8 upon s square plus 4s plus 3. So even part is s square plus 8 and odd is equal to 6s of the numerator, and in denominator even part is s square plus 3 and even part is s square plus 3 and odd is equal to 4s. So when we multiply m1 m2 minus n1 n2, we will get the equation s to the power 4 minus 13s square plus 24. Now because s is a complex frequency which is equal to j omega, when we put s is equal to j omega, the equation which we will get is equal to omega to the power 4 plus 13 omega square plus 24. Now in this equation, whatever value of omega is there, whether it is negative or it is positive, the resultant will always be greater than or equal to 0 because of the even power of this omega. So when omega is negative, then also because of this even power, omega, the value will become positive. So this resultant value is always greater than or equal to 0. So we can say that fs is positive real function. In this equation, we can check whether the function is, whether the resultant value is always greater than or equal to 0 or not. But if in any case, if any of the coefficient is negative, then it is difficult to say that for all the values of omega, the resultant value is greater than or equal to 0 or not. This is the assignment question which you have to do. So sometimes we can't say that the equation is always greater than or equal to 0 for all the values of omega. For example, if any term is negative, for example, if the equation is like minus 5 omega to the power 4 plus 5 omega square plus 40, now we can't say that for all the values of omega it will give the resultant value is always greater than or equal to 0. For such equations we have to apply Sturm test. So let's see what is Sturm test. Sturm test, in Sturm test, one Sturm constant is introduced which is equal to x, and we say that x is equal to omega square. This equation m1 m2 minus n1 n2 is equal to, we say that it is equal to a omega square. When all the coefficient of a omega square are not positive, Sturm test is needed. In this test, Sturm constant x is used which is equal to omega square. So this equation a omega square can be written as ax. Omega square is replaced by x. This test depends on the number of iterations. These iterations will continue until the iteration equation becomes independent of x. Iteration starts from I is equal to 0. So first iteration will be a0x and it is equal to ax, which we will get when we put omega square is equal to x in this equation of a omega square. In next iteration we will put I is equal to 1. So next iteration will be a1x, which is equal to dA0 upon dx. Further, the iteration can be obtained using this Sturm equation. According to Sturm equation, ai minus 2x upon ai minus 1x is equal to k1x minus k0 minus aix upon ai minus 1x. So till now we had put I is equal to 0, I is equal to 1. Now we will put I is equal to 2. When we put I is equal to 2, the equation becomes a2 minus 2, that is a0x, a2 minus 1, that is a1x, is equal to k1x minus k0 minus a2x upon a1x. So the equation 3 becomes like this. So from here we will get a2x. So to obtain a2x, we have to divide a0x up by a1x. Similarly, for next iteration, we will put I is equal to 3. When we put I is equal to 3, equation 3 becomes a1x upon a2x is equal to k1x minus k0 up minus a3 upon a2. So to get a3x, we have to divide a1 by a2x. This calculation of iteration will go on unless until the iteration becomes independent of x. Once the iteration becomes independent of x, we will stop the iteration process over there and obtain this term table. In this term table, number of iterations which are there, number of columns is depending upon number of iterations which we are getting, and 2 rows are there. In one row we will put x is equal to 0 and in other we will put x is equal to infinity. When we put x is equal to 0, we will see whether a0 is positive or negative, a1 is positive or negative, a2 is positive or negative. It will go on up to the last iteration. Last column is of number of sign changes. So here we will calculate the number of sign changes when x is equal to 0. Similarly, when x is equal to infinity, we will find out whether a0 is positive or negative, a1 is positive or negative. It will go on up to last iteration, and in last column we will find out how many times the sign are changing when x is equal to infinity. Function is said to be PRF according to Sturm test when s infinity minus s0 is equal to 0. Then only the function is PRF in nature. Let's take an example. Suppose we have to check this function, whether this function is PRF or not. For the function to be PRF, the first condition is denominator should be Hurwitz. When we check this denominator, it will come to be Hurwitz because both the quotient are positive. Second condition is applicable only when the poles are lying on the j omega axis. When we find out the poles of this function, 2 poles are there. One is lying at s is equal to minus 2 and second is lying at s is equal to minus 4. Because the poles are not on the j omega axis, so second condition is not applicable. In the third condition, m1 m2 minus n1 n2 should be greater than or equal to 0 for all the values of omega. When we solve it, we will get the equation minus 5s to the power 4 minus 5s square plus 40. Now the moment we put s is equal to j omega, the equation becomes minus 5 omega to the power 4 plus 5 omega square plus 40. Now because one of the coefficient is negative, we can't say that for all the values of omega, it is greater than or equal to 0 or not. So we have to apply Sturm test. In Sturm test, we replace omega square by x. So the equation becomes minus 5x square plus 5x plus 40 and it is equal to first iteration equation, that is a0x. Next, for next iterative equation is equal to dA0 upon dx, that is minus 10x plus 5. Next iterative equation, in that we will put I is equal to 2 and it will be obtained using this Sturm formula. When we put I is equal to 2, this Sturm equation becomes a0 upon a1 is equal to k1x minus k0 minus a2 upon a1. So to get this a2, we have to divide a0 by a1. When we divide a0 by a1, we have to divide it up to this 2 quotient. So when we divide it further up to 2 quotient, we get the remainder 165 by 4. Now this whole can be written as quotient plus remainder upon divisor. So we can write it down as x by 2 minus 1 by 4 plus 165 by 4 upon a1x. When we compare, this equation can be written as x by 2 minus 1 by 4 minus of minus 165 by 4 upon a1x. When we compare it with this equation 2, which is the Sturm equation, we see that k1 is equal to 1 by 2, k0 is equal to 1 by 4 and a2 is equal to minus 165 by 4. Now this iterative equation a2x is independent of x, so we will stop the iterative process here only. Now we will form the Sturm table. In the Sturm table, a0x, a1x, 3 iterative equations are there. When x is equal to 0, a0 is positive, a1 is positive, a2 is always negative because it is independent of x. When x is equal to infinity, a0 is negative, a1 is negative and a2 is